Well, we've introduced some important concepts of semiconductors, and these are concepts that we will build on in the next 4 units of this course. So let's spend a little bit of time and just recap what the important points were in Unit 1. So we had a set of learning objectives, and the first was just to become familiar with some basic terminology and to understand what we mean by terms such as conduction band, valence band, forbidden gap, what we mean by an electron in a hole, and intrinsic carrier concentration, those sorts of things. We wanted to be sure that we could understand the difference between a metal, an insulator, and what a semiconductor was. You should be able to explain the difference between crystalline, amorphous, and polycrystalline semiconductors. Miller indices was an important concept. You should understand Miller indices in simple cubic systems. The energy versus momentum or energy versus wave vector K relation for a semiconductor is very important. You should understand what that's all about and what those EK plots designate to us. And then finally, we talked about doping. You should understand how N-type doping works, how P-type doping works. You should also understand how the carrier concentration in a semiconductor, the concentration of electrons and holes, varies with temperature as we go from very low, almost 0 Kelvin, up to quite high temperatures. Okay, well, we began by talking about silicon as a model semiconductor, and we'll do that for most of this course. It's not the only semiconductor, but it is a good model and used for a large percentage of electronics these days. So if we have a chunk of silicon, it'll have about 5 times 10 to the 22nd atoms per cubic centimeter. If we look closely at its crystal structure in a cubic unit cell, it'll look like this. The important point to take from this, a little bit complicated crystal structure is that each silicon atom is bound in covalent bonds to 4 nearest neighbors. Okay. Silicon crystallizes not in the silicon lattice, it's called the diamond lattice. So it's the same lattice structure that diamond crystallizes in. Later on, we explained how you specify planes and directions in this unit cell using Miller indices. But the important point that we spent some time discussing is how the energy levels of an isolated silicon atom become energy bands when they're bound together in close proximity in a chunk of solid material. So these are the 2 uppermost highest energy levels of an isolated silicon atom, the valence electrons, the 3s and the 3p states. We have 4 valence electrons. When silicon crystallizes in the diamond lattice, the energy levels from adjacent silicon atoms interact and smear out and become bands. So we end up with 2 bands that accommodate all of these electrons, a valence band that is completely filled, and a conduction band that at t equals 0 is completely empty. These 2 bands of states have levels that are spaced, infinitesimally closely, so we consider the energy to be a continuous variable within the band. The 2 bands are separated by something called the band gap, E sub g, and this is also called a forbidden gap because there are no states for the electrons to reside in. An electron at that energy has no place to go. Now, at room temperature, there is some thermal energy. The atoms in this solid are vibrating with some random thermal motion. That average energy is 3/2 kT. That's an expression you've probably seen before, maybe in a freshman chemistry course for an ideal gas. That's a small number. The band gap, for silicon is much larger, 1.1 electron volts, but there is still some small probability that there will be some thermal energy sufficient to break a covalent bond, to create an empty state in the valence band, and to allow that electron, that bond that was broken, to move around and to place it in the conduction band. Obviously, when we break a bond and create a hole, a missing state, we still have the electron, so there is an equal number of electrons and holes. These are known as intrinsic charge carriers, and they're denoted by the symbol N sub I, the number of intrinsic charge carriers. Now, if we look at that in a different way, that three-dimensional crystal structure, that diamond lattice is a little complicated. We oftentimes draw these two-dimensional cartoons to understand what's happening. The key point is that the two-dimensional cartoon, the key point it conveys is that each silicon atom has 4 nearest neighbors with which it forms covalent bonds and shares electrons. The thermal energy can break one of those bonds and create a hole. Now another electron can move into that hole and the hole is moved. Another electron can move into that hole and the hole is moved again. So it has created a mobile hole that can flow throughout the semiconductor. It's an absence of a negative charge. It behaves as a positively charged particle. That covalent bond that was broken has freed up an electron, and that electron is now free to move around within the silicon lattice. So the electrons in the conduction band and the holes in the valence band can move. There's also a possibility that that electron in the conduction band can drop down into the hole in the valence band, and we annihilate the electron-hole pair. That's called a recombination process, and we'll discuss that later in the course. So let's look a little more closely at these intrinsic carrier concentrations. Remember, we said there's a small probability, say at room temperature, that a covalent bond can be broken and we can generate a hole in the valence band and an electron in the conduction band. We call these intrinsic carriers. Remember, we have 5 times 10 to the 22nd atoms per cubic centimeter in a silicon crystal. 10 to the 10th may sound like a large number, but is really a small percentage compared to the number of silicon atoms that are there. So if we look at 2 different semiconductors, silicon, which has a band gap of about 1.1 electron volts. Gallium arsenide has a larger band gap, about 1.4 electron volts. Well, the intrinsic density, carrier density in silicon at room temperature turns out to be close to 1 times 10 to the 10th per cubic centimeter. Okay. Now, in gallium arsenide, it is much lower because the band gap of gallium arsenide is significantly bigger. It takes more thermal energy to create an electron-hole pair, break one of those covalent bonds, and that means the intrinsic carrier density is going to be significantly smaller. So the things you should remember is that this intrinsic density varies exponentially with temperature and band gap. The hotter the semiconductor it is, the more covalent bonds we break, and we generate exponentially more intrinsic carriers. The higher the band gap is, the harder it is to create these intrinsic carriers. So the intrinsic number decreases exponentially with band gap, increases exponentially with temperature. Well, we all understand before we came into this course that what metals are. They're good conductors of electricity, usually good conductors of heat as well. We understand what insulators are. They're poor conductors of electricity, usually poor conductors of heat too. A semiconductor is something in the middle. Why do we want something that is not as good a conductor as metal, not as good an insulator as an insulator? Well, what makes semiconductors special is that we can dope them. We can dope them heavily and make them almost metallic. We can dope them lightly and they'll become more insulating. That's a very important capability that permits us to make semiconductor devices. Well, with these energy band diagrams, we can understand, at least qualitatively, the difference between insulators, semiconductors, and metals. An insulator has a large band gap. Very difficult to create these intrinsic electron-hole pairs. Turns out it's also difficult to dope most insulators. Semiconductors have a much smaller band gap, a moderate band gap. It's possible to create significant numbers of intrinsic carriers in them. Now, what's a metal? Well, in a metal, the band gap isn't relevant because we have a band of states that only needed to be filled up with the valence electrons halfway. And that halfway means that if an electron needs to gain some energy to move under the influence of an electric field, there's always an empty state nearby. So the band diagram for a metal looks something like this. So insulators, metals, and semiconductors. Well, we talked about the silicon lattice. So a high-quality crystal can make a high-quality semiconducting device. So crystals have long-range order. Every atom is where it's supposed to be. Now, there are also amorphous semiconductors, where there is no long-range order or periodic arrangement of the atoms. It turns out there's usually some short-range order, like even in an amorphous material, like amorphous silicon. The silicon atoms will tend to be surrounded by about 4 other silicon atoms. There's a third type of material that is widely used called polycrystalline. Polycrystalline material consists of a number of crystalline grains, but each grain is oriented differently with respect to the grains adjacent to it. What that means is that the bonds don't line up along these grains, and it's a source of defects. So what we find then is that in a polycrystalline material, there are more defects than there are in a crystalline material. Polycrystalline material is also much less expensive to produce. So it's used for applications such as solar cells, where we need large quantities of semiconductors. And as you might expect, the larger the grains, the better the material is. So we try to produce large-grained polycrystalline silicon, for example. Now, to specify directions in crystals, we use this concept called Miller indices. We spent some time discussing Miller indices, where they come from. You should feel comfortable in understanding what we mean by a 1-to-1 plane. And you should remember that a 1-to-1 direction is normal to a 1-to-1 plane. You should also be familiar with the terminology. When we use parentheses, we're referring to a specific plane. When we use the brackets, we're referring to a specific direction. But in a cubic system, there are many equivalent planes and directions. You simply rotate the crystal by 90 degrees, and you have another plane that is really the same plane. So when we use the squiggly brackets, we're talking about a set of equivalent planes. And when we use the braces like this, we're talking about a set of equivalent directions in the crystal. So take some time, be sure you're comfortable with Miller indices, because semiconductor people talk about these all the time. I'm building my device on a 100 wafer, or for example. Well, the electrons and holes move within the semiconductor, and we need to understand something about how they move. If we have a free particle in space, we know that the kinetic energy is 1/2 mv squared. We could also write that as energy is momentum squared divided by 2 times mass. Momentum is mass times velocity. Electrons and holes in a semiconductor are in a much different environment with this complicated 3-dimensional periodic potential. It's really a quantum mechanical problem. It's amazing that if you analyze the problem carefully and step back, this is one of the triumphs of semiconductor science, it turns out that there is a very simple way to understand these particles, these quantum mechanical particles in the crystal. And that is with energy versus momentum relations that are much like those for a free particle. The main difference is that the mass is replaced by an effective mass that accounts for these interactions of the electron with the periodic crystal potential of the material. In the valence band, the parabola goes down. So in that, you would think of this as a negative electron mass. If we think about them as holes instead of electrons, it's a positive hole effective mass. So the band structure, when we say band structure, we're talking about the relation between energy and crystal momentum, or energy and wave vector k. We will also be talking frequently about energy band diagrams. When we talk about energy band diagrams, we're talking about a plot of the minimum of the conduction band and the maximum of the valence band versus position, not versus momentum. So be sure you understand the difference between a band structure plot, energy versus momentum, E versus K, and an energy band plot, which is bottom of the conduction band or top of the valence band versus position. This is the simplest energy band diagram we can think of. A uniform semiconductor, the bands don't change anywhere with position. We simply show the bottom of the conduction band. There are lots of states above the bottom. And we show that top of the valence band. There are lots of filled states below the top of the valence band. We'll see more complicated energy band diagrams later on in this course. Now, electrons and holes can recombine. We'll talk about this more later in the course, but this is an energy momentum or EK plot for a direct gap semiconductor. If I've got an electron in the conduction band and a hole in the valence band, the electron can drop down from the conduction band, annihilate the hole in the valence band. The energy is given up as light. This is a recombination process in a direct gap semiconductor, and it's the basis for things like light-emitting diodes, solid-state illumination. Now, some complicated things can happen in semiconductors. The EK relation for the electrons in the conduction band might not align with the EK relation in the valence band. That is, the top of the valence band may be at a different momentum than the bottom of the conduction band. These are called indirect gap semiconductors. Indirect semiconductors produce heat when recombination processes occur. So an electron in the conduction band can recombine with a hole in the valence band. Energy will be given up, not to light this time, but to heat. It'll warm up the silicon. So we don't make efficient light emitters with indirect gap semiconductors. We need direct gap semiconductors for those purposes. Now, when we shine light on a semiconductor, we can move an electron from the valence band to the conduction band and create electron-hole pairs. This would be referred to as optical generation. We're showing it here on an EK plot. These carriers have a lot of kinetic energy. The electron is far above the bottom of the conduction band. The hole is far below the top of the valence band. That kinetic energy will be dissipated. Those carriers are frequently referred to as hot carriers because it's convenient to measure their kinetic energy by equating it to 3/2 kT. 3/2 kT is the kinetic energy of particles in random thermal motion. And these carriers are particles in random thermal motion inside the silicon lattice. Well, what happens is that excess kinetic energy is shed very quickly. Through interactions and scattering with the lattice or with other carriers, that energy is quickly relaxed and lost, and the electrons end up at the bottom of the conduction band. The hole ends up at the top of the valence band. Okay. All right, that brings us to doping. What makes semiconductors useful is that we can dope them. We can put more electrons in the conduction band or more holes in the valence band. We do that by substituting a small percentage of the silicon atoms in the lattice with an impurity. It's an impurity we intentionally put in there. So for example, if we put phosphorus or arsenic in the silicon lattice, that has 5 valence electrons. That's one extra that it needs to bond with its 4 nearest neighbors. That extra electron is bound very weakly to the phosphorus or arsenic, the N-type dopant atom. We call them donor atoms because when the small amount of thermal energy that is needed to break that bond breaks that bond and the electron is now free to wander around in the crystal, in the conduction band, we say that the dopant has donated an electron to the conduction band. If we have a column 3 dopant, gallium or boron for silicon, it has only 3 valence electrons, 1 too few. There's a missing covalent bond. There's a hole. That hole can be filled by another electron hopping into it. Now the hole is moved. So now we've created mobile holes in the valence band. These are called acceptor dopants because they accept an electron from the valence band, thereby creating a hole in the valence band. Doping is what makes semiconductors so incredibly useful. Now we can also look at doping on an energy band diagram. So here I'm showing the bottom of the conduction band and the top of the valence band. When we dope the semiconductor N-type, that 5th electron is weakly bound to the donor. We'll show that as localized states, 1 for each of the dopant atoms. So when there's a low energy, that 5th electron is there on the phosphorus atom and the phosphorus atom is neutral. But it takes a small amount of thermal energy to break that bond. Now the phosphorus atom has one too few electrons. It's now positively charged. We say it's ionized. And that electron has gone into the conduction band, and we now have an electron free to move about and carry current. We can view p-type doping on an energy band diagram as well. In this case, we introduce states a small amount of energy above the top of the valence band. That state is empty to begin with because we have one too few electrons in the valence 3 boron atom, for example. But an electron can hop up from the valence band, be accepted by that dopant. Now it occupies the dopant. But now that boron atom, for example, has one more electron than it needed to be electrically neutral. It's ionized, it has a negative charge, but we have created a positive hole that is free to move about within the silicon lattice. So doping is what makes semiconductors so useful. Now, if we take a semiconductor and we measure the mobile electron concentration in an N-type semiconductor as a function of temperature, we'll get a characteristic that looks something like this. At very low temperatures, we won't find any mobile electrons. There won't be enough thermal energy available to move an electron from the valence band to the conduction band, because that's a very significant energy. There won't even be enough thermal energy available to pull that fifth electron away from the donor atom, so we'll simply have no carriers. The semiconductor will be an insulator at very low temperatures. As we increase the temperature, we'll start to break those bonds from the phosphorus atom. We'll free those fifth electrons, those fifth valence electrons, to move into the conduction band, and the semiconductor becomes conductive. At a moderate temperature, well below room temperature for silicon, all of those bonds will be broken, and we'll have one electron in the conduction band for every donor atom in the silicon lattice. This is the region that most semiconductor devices want to operate in. If we continue to increase the temperature, we've ionized all of the donor atoms, so we won't get any more electrons there, but we can begin to have enough thermal energy to start breaking the covalent bonds and producing intrinsic electrons. So at this time, if we go to very high temperatures, the intrinsic electrons begin to overwhelm the electrons that we've created by doping. The device has gone intrinsic. We've lost the effect of the dopant atoms because the number of electrons is the same everywhere. Typically, this would cause a semiconductor device to fail if we go to temperatures that are too high. Now, at low temperatures, we call this region freeze out, because the electrons that were free to move around freeze to their phosphorus or arsenic atoms and can't move any longer. The midst region we call extrinsic, because in this region, the electron concentration is not determined by the intrinsic properties of the silicon. It's determined by the extrinsic properties of the altered silicon with its phosphorus atoms. This is generally the region that we want to operate in. If we go to high enough temperatures, then we're in what we call the intrinsic region. Now it's the intrinsic electron-hole pairs that dominate over the dopant atoms that have produced carriers. Okay, that's a summary of the concepts that you should be familiar with and that we will be building on over and over again throughout the remainder of this course, so make sure you're comfortable with these concepts. You know, the concepts, conduction, valence band, forbidden gap, and those concepts. Be sure you understand what we mean by a metal, a semiconductor, and an insulator. Understand crystalline, amorphous, and polycrystalline semiconductors. Know how to draw Miller planes, Miller directions. Given a plane, know how to deduce its Miller indices. Be sure you understand energy momentum plots for electrons or holes in crystals, or energy versus K or wave vector plots. Same thing. Also be sure you understand how they're different than an energy band diagram, which is the bottom of the conduction band versus position, top of the valence band versus position, not versus momentum. And then finally, be sure you have a good, solid understanding of doping, how it is accomplished, and then how the electron concentration or hole concentration varies with temperature as we go from very low temperatures to very high temperatures. So if you have a good, solid understanding of these concepts, you're ready for the rest of the course. And we'll discuss those topics beginning in Lecture 2.